Hello and welcome to this video. I am Karnesh Johri. This video is about templates in C++. C++ helps in expressing concepts like vector, list, map in code. These concepts are independent of data types of their elements. You can have a vector of doubles or strings or a user-defined type. Templates provide the facility for defining classes and functions with types as parameters. A single class or function template declaration can support a wide spectrum of types. This leads to compact and elegant software design. Let's look at templates in a little detail. The first topic under templates is parameterized types, which is passing of type parameters in class declarations. This is the most common usage of templates. For example, here's a declaration of class template of vector of type t. T is the type parameter. The declaration starts with the keyword template and then type parameters come in angle brackets, that is, the less than and greater than symbols. Inside the angle brackets, the keyword type name and then the type parameter, which is t here. This is followed by the class declaration where we can use the parameter t for type in data members and methods. Using this class template, we can define vector objects of different types. For example, we can say vector int v1 5000, which is a vector of 5000 ints. Similarly, we have more examples: vector char vc 200, vector of 200 characters, vector std string vs 17, vector of 17 strings, vector std list int vli 45, vector of 45 lists of integers, vector std complex double vcp3, vector of 3 complex numbers. And this is an example program using a vector class template. First, the vector class template declaration. We use a parameter type t in private data members and also in the public methods. After the class template declaration, we have an addition operator overload function for adding two vectors. This is also a template. In fact, it is a function template where type t is a parameter. The two arguments to addition function are vectors of type t, and so is the result. And in the main function, we define some vectors v0, v1, v2, etc. and do some assignment and addition operations. We can compile and run this program. It works fine. In the previous example, we have seen a class template with type parameters. We can also have value parameters for class declarations. Suppose we wish to have a C-style fixed size array, fixed array. It has two parameters, the type of element of array and the size of the array. So we declare a class template fixed array with parameter type name t, that is the type of elements, and n, which is the size of the array. And there are two constructors. The default constructor initializes elements to the default for the type of the element. The second constructor takes in an initializer list as an argument for initializing the array. And we have getVal function, which returns an element for the given array index, and a setVal function for setting an element with a given value val at the given index. And there is a print function for printing the array. In the main function, we define a fixed array with element type int and size 5, and we exercise the methods in the fixed array class. It all works fine. We have seen templates for classes. Now let's look at functions. A function implements an algorithm which is also a general concept applicable for multiple types. So it is but natural that templates can be used for functions as well. We use the same notation as before. For example, to add two numbers, we say template type name t add TATB, return a plus b. This template has one parameter type t. The type is specified at the time of function call. It can be explicitly mentioned as in the first call add int ij, or it can be implicit and is deduced from the arguments as in the second call add de. In all template usage, the types are known at compile time and there are no runtime overheads. Another example of function templates. Here we have a template with two type parameters c and t. C is the type for a container and t is type for accumulator, which keeps the sum of elements of the container. We pass a reference to a container and the initial value of the sum. The function accumulate adds all the elements of container and returns the sum. We can call the accumulate function with reference to different containers and different types of sum variable, and it returns the sum of all the elements added to the initial value. The next topic is function objects, also known as functors. As the name function object suggests, it is an object of a class and it is also a function. It is an object which can be called as a function. How does that happen? The underlying class implements the function call operator parenthesis. For example, we have a class which finds whether an argument is less than a fixed value, template type t, class less than, constant t val. This is the value to compare against, and the public members, constructor less than constant t reference v, val initialized to v, and the class implements the function call operator, bool operator, parenthesis, constant t reference, x, constant, return x is less than val. The key difference between functors and functions is that functors have state information in the form of data members, which is not there in functions. For example, we have constant t-val here, the value to compare against. We can initialize objects of less than functor. The first is less than int 49, which has an integer 49, and the next is less than std string lts apricots, which has a string with value apricots. We can use these functors in our program. Suppose we wish to count the number of elements in a container that meet the functor criteria, that is, the elements for which the functor is true. We can do something like this. We have a function template count with two type parameters c and p. C is the type of container and p is a predicate, a Boolean expression that evaluates to false or true. We can use functor as a predicate. In the main function, we have a vector of integers vi and we wish to know how many elements of vi are less than 29. So we call the count function with container vi and functor less than integer I, where I is 29. Similarly, we have a list of strings ls and we wish to know how many elements of ls are less than the string nectar. So we call count with container ls and functor less than string s, which is nectar, and count returns the number of elements of list less than nectar. In the preceding example, we have used functor as an argument to function count. It plays an important role in the way count works. We have used the functor template less than. We could have used a different functor like greater than, equal to, etc. and got the count function to work differently and give a different output. The point is that functors are often used as arguments to functions, and they play an important role in the way the use function works. For example, here we use the stdsort function for sorting vector v first in the descending order and then in the ascending order. Both descending and ascending are functors which are passed as arguments to the sort function. Back to our example, we have used a functor as a parameter to the count function. We set the functor state in the constructor. The functor state variables are integer I in the first case and the string s in the second case. A lambda expression is a shortened notation for an anonymous functor call. Here we have replaced functors with lambda expression in the example code. Comparing the two, in case of functors, we need to create a functor using a constructor and then use it in a function like count. In case of lambda expressions, we can just put it in place where required and the job is done. In both cases, the code is inlined so the overheads are minimal. Looking at a lambda expression, there are three distinct parts. The first is the capture list in square brackets. The second is an optional parameter list in parentheses. And the third is the body in braces, which is the lambda expression code to be executed. The capture list is for capturing the local variables in the function, similar to creating the state in functors. The rules for capturing local variables are like this. If the capture list is empty, nothing is captured. If there is just an ampersand in the capture list, all local variables are implicitly captured by reference. If there is just an equal sign in the capture list, all local variables are implicitly captured by value. If there is a capture list where variables are listed explicitly, only those listed are captured. Variables preceded with an ampersand are captured by reference and the others are captured by value. Ampersand comma capture list implicitly capture all variables by reference except those in the capture list which are captured by value. Equal to comma capture list implicitly capture all local variables by value except those in the capture list which are captured by reference, and these variables in the capture list must be preceded by an ampersand. Next we have parameters with types in parentheses. For each call of lambda expression, these parameters need to be passed. And finally, the body comprising of code which is executed when the control reaches the lambda expression. Variadic templates are templates that allow variable number of type parameters, that is, template type name t, type name ... rest. The three dots after type name indicate that there are 0 or more type parameters. And we can have a function template using a variadic template, that is, template type name t, type name ... rest, void f t first rest ... rest, and the function body g first f rest ... The key to handling a variadic template is that the first type parameter is separated from the rest. As you can see, the definition of function f, there is t first, the first argument, and the rest of arguments. We process the first argument in the function g, the call g first, and then call the function f itself recursively with the rest of arguments. Eventually, there are no arguments left and function f is called with no arguments. To take care of that, we have a definition of function f with empty body, that is void f braces, and the recursion terminates. We have an example program using a variadic template, and it is like this. First, we have a function template for function g, which just prints the argument on the standard output. Then we have the empty function f for terminating the recursion, and then the variadic function template. The function f calls function g with the first parameter, which does the processing of one parameter, and then function f calls itself with the rest of parameters. In the main function, we call function f with some random arguments, and this is done twice. We can compile and run this program. It works fine. An alias is a different and more convenient name for something. In traditional C and C++, we have type def, which is something like this. Type def unsigned int size t. This makes size t a synonym of unsigned int. We can define variable I of type size t. Actually, size t is not a new type. It is just a synonym for unsigned int, and we can print its size using the size of operator. That's the old way of doing things. Starting with C++11, there's a better way of doing this, and it is the using declaration. We can say using size u equal to unsigned int. That makes size u a synonym of unsigned int. Then we can define a variable j, size uj, and we can use j in the code. Now consider this template. Template type name t, class vector, public, using value type equal to t. Here value type is an alias for template parameter type t. It is an alias for type of elements of vector. The standard library follows this convention that value type gives the type of the elements of a standard library container. For a container C, we can define a template alias using value type equal to type name C value type. Then value type C gives the type of element of container C. Here is an example for template alias. We define value type as an alias for type name C value type, and the function template sum adds all the elements of container C, and the result is stored in a variable of appropriate type, which is the type of elements of the container. In the main function, we call sum with a vector of integers, vector of strings, and a list of strings, and it adds up all the elements. We have seen how templates help in declaring classes with type and value parameters. You can find all this information at SoftPlayog website. Here's a QR code, and the link is there in the description. Please subscribe to SoftPlayog channel, click on the bell icon and enable notifications. Thanks very much for watching. Take care and stay safe.